Hello, everyone. Today, Wenchen and I are glad to share with you the latest updates about the upcoming release, Spark 3.0. So I'm Xiaoli. Both Wenchen and I are working for Databricks. So we focus on the open source developments. Both of us are Spark committer and PMC members. Databricks provides a unified data analytics platform to accelerate your data-driven innovation. We are a global company with more than 5,000 customers and across various industries. And we have more than 450 partners worldwide. And most of you might have heard of the Databricks as an original creator of the Spark, Data Lake, MLflow, and Coalesce. These open source projects that are leading the innovation in the fields of data and machine learning. We continue to contribute and nurture this open source community. In Spark 3.0, the whole community resolved more than 3,400 JIRAs. Spark SQL and the core are the new core module, and all the other components are built on Spark SQL and the core. Totally, the pull requests for Spark SQL and the core constitute more than 60% in Spark 3.0. In the last few releases, the percentage keeps going up. Today, we will focus on the key features in both Spark SQL and the core. This release delivered many new capabilities, performance gains, and extended compatibility for the Spark ecosystem. This is a combination of the tremendous contributions from the open source community. It is impossible to discuss the new features within 16 minutes. We resolved more than 3,400 JIRAs. Even in this slide, I did my best, but I only computed 24 new Spark 3.0 features. Today, we would like to present some of them. First, let us talk about the performance-related features. High performance is one of the major advantages when people select Spark as their computation engine. This release keeps enhancing the performance for interactive, batch, streaming, and ML workloads. Here, I will first cover 4 of the performance features in SQL query compilers. Later, Wenchen will talk about the performance enhancement for the built-in data sources. The 4 major features in query compilers include a new framework for adaptive query execution and a new runtime filtering for dynamic partition pruning. And also, we greatly reduce the overhead of a query compiler by more than a half, especially on the optimizer overhead and the SQL cache synchronization. Supporting a complete set of junkins is another useful feature many people are waiting for. Adaptive query execution was available at the previous releases. However, the previous framework has a few major drawbacks. Very few companies are using it in the production systems. In this release, Databricks and Intel worked together and redesigned the new framework and resolved all the known issues. Let us talk about what we did in this release. Michael Umbers. He is the creator of Spark SQL and also Catalyst Optimizer. In the initial release of Spark SQL, all the optimizer rules are heuristic-based. To generate good query plans, the query optimizer needs to understand the data characteristics. Then, in Spark 2.x, we introduce a cost-based optimizer. However, in most cases, data statistics are commonly absent, especially when statistics collection is even more expensive than the data processing itself. Even if the statistics are available, the statistics are likely out of date. Based on the storage and the compute separation in Spark, the characteristics of data arrival is unpredictable. The costs are often misestimated due to the different deployment environment and the black box user-defined functions. we are unable to estimate the cost for the UDF. Basically, in many cases, Spark Optimizer is unable to generate the best plan due to this limitation. For all these reasons, runtime adaptivity becomes more critical for Spark than the traditional systems. So this release introduced a new adaptive query execution framework called A2E. The basic idea of adaptive planning is simple. We re-optimize the execution plan using the existing rules of the optimizer and the planner after we collect more accurate statistics from the finished plan nodes. The red line shows the new logics we added in this release. Instead of directly optimizing the execution plans, we send back the unfinished plan segments and use the existing optimizer and planner to optimize them again and build a new execution plan. This release includes 3 adaptive features. We can convert the submerged join to broadcast hash join based on the runtime statistics. We can shrink the number of reducers after over-partitioning. We can also handle the skew join at the runtime. If you want to know more details, please read the blog post I posted here. Today, I will briefly explain them one by one. Maybe most of you already learned many performance tuning tips. For example, to make your join faster, you might guide your optimizer to choose a broadcast hash join instead of the submerged join. You can increase the spark.sql.auto broadcast join threshold or use a broadcast join hint. However, it is hard to tune it. You might hit out of memory exceptions and even get the worst performance. Even if it works now, it is hard to maintain over time because it is sensitive to your data workloads. You might be wondering why Spark is unable to make the best choice by itself. I can easily list multiple reasons. Like what we said before, the statistics might be missing or out of date. The file is compressed. The file format is column-based, so the file size does not represent the actual data volume. And also the filters could be complex. And they might also contain the black box UDFs. The whole query fragments might be large, complex, and it is hard to estimate the actual data volume for Spark to make the best choice. So this is an example to show how A2E converts a submerged join to a broadcast hash join at the runtime. First, execute the leaf stages in a query and collect the statistics from the shuffle operators, which materialize the query fragments. You can see the actual size of stage 2 is much smaller than the estimated size, reduced from 30 megabyte to 8 megabyte. So we can optimize the remaining plan and change the join algorithm from submerged join to broadcast hash join. Another popular performance tuning tip is to tune the configuration spark.sql.shuffle.partitions. The default value is a magic number 200. Previously, the original default is 8. Later, it was increased to 200. I believe no one knows the reason why it becomes 200 instead of 50, 400, or 2000. It is very hard to tune it, to be honest. Because it is a global configuration, it is almost impossible to decide the best value for every query fragment using a single configuration, especially when your query plan is huge and complex. If you set it to very small value, the partition will be huge. And the aggregation and the sort might need to spill the data to the disk. If the configuration value is too big, the partition will be small. But the number of partitions is big. It will cause inefficient I/O, and the performance bottleneck could be the task scheduler. Then it will slow down everybody. Also, it is very hard to maintain over time. A2E can solve it in a smart way. We can first increase the initial partition number to a big one. After we execute the leaf query stage, we can know the actual size of each partition. Then we can automatically coalesce the nearby partitions and automatically reduce the number of partitions to a smaller number. This example shows how we reduce the number of partitions from 50 to 5 at the runtime. And we added the actual coalesce at the runtime. One more popular performance tuning tip is about the data steal. Data steal is very annoying. You could see some long-running or frozen tasks and a lot of disk spilling and a very low resource utilization rate in most nodes, and even out of memory. Our Spark community might tell you many different ways to solve such a typical performance problem. You can find the steal values and the right queries to handle the steal value separately. And also you can add the actual steal keys that can remove the data steal, either new columns or some existing columns. Anyway, you have to manually rewrite your queries, and this is annoying. And sensitive to your workloads too, which could be changed over time. This is an example. Without a steal optimization, because of data steal after the shuffle partition A0 will be very large. If we do a join on these two tables, the whole performance bottleneck is to join the values for this specific partition A0. For this partition A0, the cost of shuffle, sort, and merge are much bigger than the other partitions. Everyone is waiting for the partition 0 to complete. It slows down the execution of the whole query. Our adaptive query execution can handle it very well in the data steal case. After executing the leaf stages, stage 1 and stage 2, we can optimize the queries with a steal shuffle reader. Basically, it will split the steal partitions into a smaller subpartitions after we realize some shuffle partitions are too big. Let us use the same example to show how to resolve it using adaptive query execution. After realizing a specific partition is too large, A2E will add a steal reader to automatically split the table A's partition part 0 to 3 segments, split 0, split 1, and split 2. Then it will also duplicate another side for table B. Then we will have 3 copies for the table B's part 0. After this step, we can parallelize the shuffle reading, sorting, merging for this big partition A0. We can avoid generating a very big partition for the submerge join. Overall, it will be much faster. Based on a terabyte TPCDS benchmark without statistics, Spark 3.0 can make Q77 8 times faster and also achieve 2 times fast and speed up for Q5 and more than 1.1 speed up for another 26 queries. So this is just a beginning. In the future releases, we'll continue to improve the compiler and introduce more new adaptive rules. The second performance features I want to highlight is a dynamic partition pruning. So this is another runtime optimization rule. Basically, dynamic partition pruning is to avoid partition scanning based on the query results of the other query fragments. It is important for the star schema queries. We can achieve a significant speed up in TPCDS queries. So this is a number. In the TPCDS benchmark, 60 out of 102 queries shows a significant speed up between 2 times and 18 times. It is to prune the partitions the joins read from the fact table T1 by identifying those partitions that result from filtering the dimension table T2. Let us explain it step by step. First, we'll do the filter pushdown in the left side. And on the right side, we can generate a new filter for the partition column PT because the join P is a partition column. Then we get the query results of the left side. We can reuse the query result and generate the list of the constant values DPP filter result. Now we can push down the in filter in the right side. This will avoid scanning all the partitions of the huge fact table T1. For this example, we can avoid scanning 90% of partitioning. With this dynamic partition pruning, we can achieve 33 times speed up. So the last performance feature is join hint. Join hints are very common optimizer hints. It can influence the optimizer to choose the expected join strategies. Previously, we already have a broadcast hash join. In this release, we also add the hints for the other 3 join strategies: submerge join, shuffle hash join, and the shuffle density loop join. Please remember, this should be used very carefully. It is difficult to manage over time because it is sensitive to your workloads. If your workloads patterns are not stable, the hints could even make your query much slower. Here are examples of how to use these hints in the SQL queries. You also can do the same thing in the DataFrame API. When we decide the join strategies, I list the difference here. So the broadcast hash join requires one side to be small, no shuffle, no sort, so it performs very fast. For the shuffle hash join, it needs to shuffle the data, but no sort is needed. So it can handle the large tables, but will still hit out of memory if the data is skewed. Submerge join is much more robust. It can handle any data size. It needs to shuffle and sort the data, slower in most cases when the table size is small compared with a broadcast hash join. And also shuffle nested loop join, it doesn't require the join keys, unlike the other 3 join strategies. To enable new use cases and simplify the Spark application development, this release delivers a new capability and enhance the existing features. Let's first talk about the Pandas UDF. This is a pretty popular performance features for the PySpark users. So let us talk about the history of the UDF support in PySpark. In the first release of Python support, 2013, we already support the Python Lambda functions for RDD API. Then in 2014, users can register Python UDF for Spark SQL. Starting from the Spark 2.0, Python UDF registration is session-based. And then next year, users can register and use Java UDF in Python API. In 2018, we introduced the Pandas UDF. In this release, we redesigned the interface for Pandas UDF by using the Python type hints and add more types for the Pandas UDFs. To address the complexity in the old Pandas UDFs, from Apache Spark 3.0 with the Python 3.6 and above, Python type hints such as the pandas.series, pandas.different, tuple, and the iterator can be used to express the new Pandas UDF types. For example, in Spark 2.3, we have a Scala UDF. The input is the pandas series, and the output is also pandas series. In Spark 3.0, we do not require users to remember any UDF types. You just need to specify the input and output types. In Spark 2.3, we also have a group map pandas UDF. The input is a pandas different, and the output is also pandas different. This slide shows the difference between the old and the new interface. The same here. The new interface can also be used for the existing group aggregate pandas UDFs. In addition, the old pandas UDF was split into 2 API categories, pandas UDFs and the pandas function APIs. You can treat the pandas UDFs in the same way that you use the other PySpark column instance. For example, here, calculate values. You are calling the pandas UDF calculate. We do support the new pandas UDF types from iterators of series to iterate of the series, and from iterators of multiple series to iterator of series. So this is useful for comprehensive state initialization of your pandas UDFs, and also useful for pandas UDF pipeline. However, you cannot use a pandas function APIs with this column instance. Here are these two examples, map pandas function API and call group map pandas UDF APIs. These APIs are newly added in this release. So next, Wenchen will go over the remaining features and provide a deep dive into accumulator-aware scheduler. Please welcome Wenchen.
Thanks, Xiao, for the first half of the talk. Now let me take over from here and introduce the remaining Spark 3.0 features. I will start with the Accelerator-Aware Scheduler. In 2018 Spark Summit, Linode announced the new project Hydrogen. Accelerator-Aware Scheduler is part of this project. It can be widely used for accelerating special workloads. In this release, we support stand-alone, YARN, and Kubernetes scheduler backend. So far, users need to specify the required accelerator resources using application-level configs. In the future, we will support the job, stage, and task levels. To further understand this feature, let's look at the workflow. Ideally, the cluster manager shall be able to automatically discover resources like GPUs. When the user submits an application with resource request, Spark shall pass the resource request to cluster manager. And then the cluster manager collaborates to allocate and launch executors with the required resources. After Spark job is submitted, Spark shall schedule tasks on available executors. And the cluster manager should track the resource usage and perform dynamic resource allocation. For example, when there are too many pending tasks, the cluster manager should allocate more executors to run more tasks at the same time. When the task is running, the user should be able to retrieve the assigned resources and use them in their code. In the meanwhile, cluster manager should monitor and recover failed executors. Now let's look at how can the cluster manager discover resources and how can users request resources. As an admin of the cluster, I can specify a script to auto-discover accelerators. The discovery script can be specified separately on the driver and the executors. We also provided an example to auto-discover NVIDIA GPU resources. You can adjust this example script for other kinds of resources. Then, as a user of Spark, I can request resources at the application level. I can use the config spark.executor.resource name, the amount, and the corresponding config for Java to specify the accelerators amount on the driver and executors. Also, I can use the config spark.task.resource name, the amount, to specify the accelerators required by each task. As I mentioned earlier, we will support more fine-grained level later, like the job or stage level. Please stay tuned. Next, let's see how you can leverage the assigned accelerators to actually accelerate your workloads, which is probably the most important part to the users. So as a user of Spark, I can retrieve the assigned accelerators from the task context. Here is an example in PySpark. The context.resources returns a map from the resource name to resource info. In the example, we request for GPUs, and we can get the GPU address from the resource map. Then we launch the TensorFlow to train my model using GPUs. Spark will take care of the resource allocation and isolation, and also monitor the executor health for failure recovery, which makes my life much easier. As I mentioned earlier, the accelerator-aware scheduling support has been added to stand-alone, YARN, and Kubernetes cluster manager. You can check these Spark Jira tickets to see more details. Unfortunately, the method support is still not available. We really appreciate it if any methods expert has interest and is willing to help the Spark community to add the method support. Please leave a comment in the Jira ticket if you want to work on it. Thanks in advance. Last but not the least, we also improved the Spark Web UI to show all the discovered resources on the executor page. In this page, we can see that there are GPU 0 available on the executor 1. You can check the web UI to see how many accelerators are available in the cluster, so you can better schedule your jobs. In this release, we also introduced 32 new built-in functions and add high-order functions in the Scala API. The Spark community pays a lot of attention to usability. We have investigated many other SQL systems like the PostgreSQL and implemented many commonly used functions in Spark. Hopefully, these new built-in functions can make it faster to build your queries, as you don't need to waste time to run a lot of UDFs. Due to the time limitation, I can't go over all the functions here, so let me just introduce some map type related functions as an example. When you deal with map type values, it's common to get the keys and values from the map as an array. There are two functions, map keys and map values, can do this for you. The example is from the Databricks runtime notebook. Or you may want to do something more complicated, like getting a new map by transforming the original map with the keys and map values functions. So there are two functions, transform keys and transform values, can do this for you. And you just need to write a high-order function to specify the transformation logic. As I mentioned earlier, the high-order functions also have Scala APIs rather than the SQL API. Here is an example about how to do the same thing with the Scala APIs. You can just write a normal Scala function, which takes the current objects as the inputs. They have the same effect as the SQL API. This release also includes many enhancements that makes the monitoring more comprehensive and stable. They can make it easier to profile and debug your Spark applications. The first feature I want to talk about is the new UI for the jar streaming. Here is the GIF to show it. Jar streaming was initially introduced in Spark 2.0. This release adds the dedicated Use Spark Web UI for inspection of these streaming jobs. This UI offers two sets of statistics. One, aggregated information of completed streaming queries, and two, detailed statistics information about the streaming query, including the input rate, process rate, input loss, batch duration, operation duration, and others. More specifically, the input rate and the process rate means how many records per second the streaming source produces and the Spark streaming engine processes. It can give you a sense about if the streaming engine is fast enough to process the continuous input data. Similarly, you can tell it from the batch duration as well. If many batches takes more time than the micro batch interval, it means the engine is not fast enough to process your data, and you may need to enable the backpressure feature to make the source produce the data slower. And the operation time is also a very useful metric. It tells you the time spent on each operator so that you can know where is the bottleneck in your query. We also have many different enhancements in DDL and DML commands. Let me talk about the improvements in the explain command as an example. This is a typical output of the explain command. You have many operators in the query plan tree, and some operators have a lot of additional information. Reading plans is critical for understanding and tuning queries. The existing solution looks calculated, and the string of each operator can be very wide or even truncated. It becomes wider and wider in each release as we add more and more information in the operator to help debugging. This release, we enhance the explain command with a new formatted mode and also provided a capability to dump the plans to the files. You can see it becomes much easier to read and understand. So there is a very simple plan tree at the beginning, then follows a detailed section for each operator. This makes it very easy to get an overview of the query by looking at the plan tree. It also makes it very easy to see the details of each operator as the information is now stacked vertically. At the end, there is a section to show all the subqueries. In the future releases, we will add more and more useful information for each operator. This release, we also introduced a new API to define your own metrics to observe data quality. Data quality is very important to many applications. It's usually easy to define a metrics for data quality by some upgrade functions, for example, but it's also hard to calculate the metrics, especially for streaming queries. For example, you want to keep monitoring the data quality of your streaming source. You can simply define the metrics as the percentage of the error records. Then you can do two things to make it happen. One, call the observe method of the streaming data frame to define your metrics with a name and a start the stream. So in this example, the name is data quality, and the metrics is just we count the error records and see how many percent of it in the total records. Two, you add a listener to watch the streaming process events and get your metrics by the name and do whatever you want to do, such as sending an alert email if there are more than 5% error data. Now let's move to the next topic. SQL compatibility is also super critical for workloads migrated from the other database systems to Spark SQL. In this release, we introduced the ANSI storm assignment policy for table insertion. We added runtime overload checking. We respect the ANSI resolved keywords in SQL parser. We also switch the calendar to the widely used calendar, which is the ISO and SQL standard. Let's look at how the first two features can help you to enforce data quality. A little more about the storm assignment. It's something like assigning a value to a variable in programming language. In the SQL world, it is table insertion or upsert, which is kind of assigning values to a table column. Now let's see an example. Assume there is a table with two columns, I and j, which are type int and type string. If we write an int value to the string column, it's totally okay, it's totally safe. However, if we write a string value to the int column, it's risky. The string value is very likely to not be an integer form, and Spark will fail and warn you about it. If you do believe your string values are safe to be inserted into an int column, you can add a cast manually to bypass the type check in Spark. We can also write long type values to the int column, and Spark will do the overflow check at the wrong time. If your input data is invalid, Spark will throw an exception at the wrong time to tell you about it. In this example, the integer 1 is okay, but the larger value below can't fit the integer type, and you will see this error if you run this table insertion command, which tells you about the overflow problem. Also, this release enhances the built-in data sources. For example, for package data source, we can do column pruning and filter pushdown for nested columns. Also, we support filter pushdown for CSV files. This release also introduced a new binary data source and also a new OP data source for testing and benchmarking. Let me further introduce the organization of nested columns in Parquet and Oak data source. The first one is column pruning. For columnar file format like Parquet and Oak, we can skip reading some useless data blocks if they don't contain the columns we need. This technique can be applied to nested columns as well in Spark 2.0. To check if your query, in Spark 3.0, to check if your query can benefit from this optimization or not, you can run the explain command and see if the read schema of the file scan node strips the unselected nested columns. In this example, only the nested column A is selected, so the read schema only contains A. Filter pushdown is also a very popular technique to save disk I/O when reading files. Similarly, you can also check the explain result and see if the push filters of the file scan node contains the nested column filters. In this example, we do have a filter with the nested column A, and it does appear in the push filters, which means this operation happens in this query. This release also spends a lot of efforts on the extensibility and ecosystem, like the DSV2 API improvements, Java 11, Hadoop, and Hive 3 support. Let me first talk about the DSV2 API. This release extends the DSV2 API by adding the catalog plugin. The catalog plugin API allows users to register their own catalog implementations and take over the metadata operations from Spark. This can give end users a more seamless experience to access external tables. Now, end users just need to register the catalog once and then access and manipulate the tables in the catalog directory, while before, end users have to register each table. For example, let's say you have registered a MySQL connector as catalog named MySQL. you can use select to read data from an existing MySQL table. You can also insert into a MySQL table with Spark's table views. You can also create and alter tables in MySQL with Spark, which is not possible before, because before we don't have the catalog plugin. Now that this example will be available in Spark 3.1 when we finish the JDBC v2 DSLs. Some people may have a question. Now Spark has both DSLs v1 and v2 APIs. Which one should I use? In general, we want everyone to move to DSL v2 at the end, but the v2 API is not ready yet, as we need more feedbacks to polish the API. Here are some tips about when to pick the v2 API. So if you want to provide the catalog functionalities, then you have to use v2 because v1 API doesn't have this ability. If you want to support both batch and streaming in your DSLs, then you should use v2 because in v1, the streaming and batch are different APIs, which makes it harder to reuse the code. And if you are sensitive to the scan performance, then you can try the v2 API because it allows you to report the data partitioning to skip shuffles in Spark, and also it allows you to implement the vectorized reader for better performance. If you don't care about this stuff and just want to write a DSL once and never change it, please use the v1 API as it's very stable. The big data ecosystem also evolves very fast. In this release, Spark can be better integrated into the ecosystem by supporting the newer version of these common components like Java 11, Hadoop 3, Hive 3 Metastorm, and Hive 2.3 execution. I want to mention some breaking changes here. Starting from this release, we only build Spark with Scala 2.12, so Scala 2.11 is no longer supported. And we deprecate Python 2 because it is end of life. In the download image, we prebuild Spark with different Hive and Hadoop combinations. By default, it will be Hadoop 2.7 and with Hive 2.3 execution. There are another two combinations of previews available. One is Hadoop 2.7 and Hive 1.2 execution, which is for people who can upgrade their platforms. The other is Hadoop 3.2 and Hive 2.3 execution, which is for people who want to try Hadoop 3. We also extend the support for different Hive Metastorm versions from 0.12 to 3.1. Documentation improvements is the last exciting news I want to share with everyone. How to read or understand the web UI is a common question to many Spark users. This is especially true for Spark SQL users and Spark streaming users. They are using the high-level APIs. They usually don't know what are IDDs and what are jobs, stages, and tasks. Also, the UIs are using many terminologies and metrics names, which are not very clear to many users. Starting from this release, we add a new section for documenting the web UI. It includes the basic job, stage, and task UIs, and also SQL streaming JDBC UIs. This is just a start. We will continue to enhance it. Then SQL reference. Finally, this release added the SQL reference for Spark SQL. Spark SQL is the most popular and important component in Spark. However, we did not have our own SQL reference to define the SQL semantic and detailed behaviors. Let me quickly go over the major chapters in the SQL reference. So we have a page to explain the NC compliance of Spark. So as I mentioned before, we have the we have SQL compatibility, but to avoid breaking the existing queries, we make it optional. So you can only enable the NC compatibility by enabling this flag. We also have a page to explain the detailed semantic of each data type, so you can know what they mean and what's the behavior of them. We also have a page to explain the data pattern strings used for formatting and parsing functions of JSON and CSV data sources. There's also a page to give the document for each functions in the Spark. We also have a page to explain the syntax, how to define the table or function identifiers. Also, there's a page to explain the syntax and the semantic of each letter syntax in Spark SQL. Also, there's a page to explain the non-semantic. The non is a very special value in Spark SQL and other SQL systems. So there must be a page to detail explain what's the meaning of non in the queries. Also, we have a page to explain the syntax for other commands like DDL and dman commands. And also insert is also included in the document, same as select. So State has so many features, so we want to have a page to expand all of them. Yeah, there are also a page for other special commands like show tables. Finally, the mapping guide. This is another critical enhancement in Spark 3.0 document. In this release, all the components have the mapping guides. When you upgrade your Spark version, you can read them carefully and find all the breaking changes. You might be wondering why it is much longer than the previous version. It's because we try to document all the important breaking changes you want to hit. If you upgrade, hit some errors that are not well documented or some confusing error messages, please open a ticket and we will try to fix them in the subsequent maintenance releases. Now that Spark is almost 10 years old now, the Spark community is very serious about breaking changes, and we try our best to avoid silent query without changing. If you upgrade to Spark 3.0 this time, you may see explicit error messages about query without changing. The error message also provides config names for you to either go back to the legacy behavior or go with the new behavior. In this talk, we talked about many exciting features and improvements in Spark 3.0. Due to the lack of time, there are still many other nice features not being covered by this talk. Please download Spark 3.0 and try it yourself. You can also try the latest LibreX Runtime 3.0 beta. All the new features are already available. The community edition is for free. Without the contributions by the home community, it is impossible to deliver such a successful release. Many thanks to all the Spark contributors all over the world. Thank you everyone.